Shambit, please.
Good afternoon, everyone. Today's speaker, Dr. Sayantan Chakraborty, is an assistant professor in the Earth Sciences, Earth System Science, and Engineering Division of the Department of Civil Engineering at IIT Guwahati. He did his PhD in structural geology and tectonics and MSc in applied geology from the Department of Earth Sciences, IIT Bombay. He did his BSc in geology honors from the Department of Geology of erstwhile Presidency College, Kolkata. Essentially, we can say Dr. Shantanu Chakraborty is a structural geologist with a keen interest in shear zones and how they affect the crustal architecture, fluid flow, and seismicity in orogens, with a special emphasis on the Himalaya and Indo-Burma wedge. He has more than 10 years of experience of working on the Himalayan metamorphic core in Sikkim, Eastern Himalaya, and has well cited publications in frontline journals like Journal of Geology, Tectonophysics, Journal of Structural Geology, and so on in his credit. His current research interest, I would say, lies in studying and understanding aseismic creep behavior of fault zones. So, with this brief introduction, I would like to request Dr. Shantanu Chakraborty to begin with his discourse. Sir, please.
Thank you so much, Shamvit, for this very nice introduction. I'm humbled, and thank you, Professor Dasgupta, for giving me an opportunity to speak in front of the students about the research that I have been doing or that I plan to carry on in the near future. So without further ado, I'll just start about the talk. So the topic that I'm going to discuss today is based on the main central thrust. If I could just get it started. Is my screen visible to everyone?
Yeah.
Okay, thank you. So the topic of my talk will be decoding the enigma of the main central thrust in the Himalaya, and the approach that we have used in this study is a shear zone geometry based approach.
Shantan, please make it full screen.
It is full screen in my
Oh, okay. Please proceed.
Okay, so over the course of the next 45-50 minutes, I am going to talk about 5 different topics. First, I'll give a brief introduction about the historical context of the Himalaya and the main central thrust in general, which we also call as the MCT. Then I am going to introduce the objectives and the rationale behind the study. Then I'm going to discuss the major findings from the study. I'm going to conclude with the major takeaway points. And in brief, I am going to discuss about the future direction of research in the Himalaya. So let us start with the historical context. So the Himalaya, as we know, is a continental collisional orogen, which started forming about 59 million years ago due to the collision between the Eurasia plate and the Indian plate, and it extends for 2,500 kilometers from the Hazara syntaxis in the west to the Namche Barwa syntaxis in the east. If we take a section across the Himalaya, we would see that it consists of major shear zones and fault zones. In the northernmost part of the Himalaya, we have the South Tibetan Detachment System, which is a series of normal faults affecting the Tethyan sediments and the upper part of the Greater Himalayan sequence. Then we have the main central thrust, or the MCT, which separates the Greater Himalayan rocks from the lower Lesser Himalayan rocks. Then we have the Ramgarh thrust. The Munshiari thrust is not shown in the figure. The Munshiari thrust features between the MCT and the Ramgarh thrust. Then further south, we have the main boundary thrust and the main frontal thrust. You have to also know that all of these faults, they soil into a basal décollement, which is called as the main Himalayan thrust, which results in the major earthquake within the Himalaya. Now, the main central thrust and the Greater Himalayan sequence have been studied extensively. So majority of the papers, if you read from the Himalaya, majority of them would focus on the MCT and the Greater Himalayan sequence. However, there is a lack of understanding of this region because primarily due to the controversy surrounding the definition and the position of the MCT. Now, before we understand that controversy, we have to look at two competing models which became very prominent in the late 90s and early 2000s, which resulted in the MCT becoming the limelight of the Himalayan research. One of them is on the left-hand side, as we can see, it is called the channel flow model. The channel flow model suggested that the South Tibetan detachment system and the main central thrust, they acted coevally, resulting in movement of partially molten layers from the lower part of Tibet plateau, and it came and froze as a frozen channel, resulting in the formation of the Greater Himalayan sequence. And this model became so popular in the early 2000s that a lot of research was carried out on the South Tibetan detachment system and the MCT, and it brought a lot of limelight to these particular structures. Another model which became very important at this stage was the...
Sayantan, sorry for the interruption. The slide is not changing.
Okay, it is changing in my machine. I don't know what is...
You can share your entire screen, so that would be okay, I think.
Okay. Is it visible now?
Yes, it is visible now.
Okay. Yeah. So, coming to the second model, which is known as the accreted terrain model, if we look at the Greater Himalayan sequence, it has isotopic signatures which is very different to the lower lesser Himalayan rocks. And it has a younger age than the lower lesser Himalayan rocks. Now, the conventional thrust model suggests that the older rocks are juxtaposed over younger rocks by thrusts, but that is not the case in case of the Greater Himalaya, which led Peter Dissels and his team to suggest that the Greater Himalayan sequence is an accreted terrain and the main central thrust is a reactivated paleosuture zone. Now, these two competing models, they thrusted the main central thrust into the limelight, and a lot of research has since been carried out on the MCT. But there is a lot of problems associated with the MCT. The first problem being that what is its definition and what is its position? Now, the original definition of the MCT was that it was a thrust carrying the GHS Nisus over the LHS schist. This was proposed by Heim and Ganser back in 1939. Now, the problem with this definition is, along major parts of the Himalaya, we don't see any clear schist-gneiss contacts. The rocks in its vicinity are deformed and have amphibolite facies metamorphism. And the structural break associated with the MCT is not very clear-cut. This has led to the use of several alternative methods or non-structural methods like changes in lithology, isotope signatures, metamorphic grade, and ages. Now, the problem with these different alternative definitions is that they are contrasting with each other and resulted in the non-unique positioning of the MCT, which varies up to 5 km structural distance, which hinders regional correlation. One of the regions which has suffered significantly from this problem is in Sikkim, in eastern Himalaya. Now, if we look at the geological map of Sikkim, this is a simplified geological map of Sikkim, where the orange color unit represents the Greater Himalayan sequence, the purple color rocks, they represent the Lesser Himalayan crystalline sequence, and the sky blue colored rocks, they represent the unmetamorphosed Lower Lesser Himalayan sequence. And the boundary between the Greater Himalayan sequence and the Lesser Himalayan crystalline sequence was based on the isotopic signature study of Mottram et al. And these dash dot structures that you see, these are the different MCTs that have been proposed by different workers in Sikkim. And each of them vary from each other by about 12 km structural distance. Now, this brings us to the first problem, that is, where is the MCT located and what is its geometry? And usually we know that large-scale shear zones like the MCT, they are conduits to fluids. So until and unless we know where the MCT is located, we don't even know what role did fluid play in its deformation. The second problem that we have is that are there any major shear zones in its proximity? And if so, what are their geometries? And finally, we also don't know what is the relative timing of activity of these shear zones and what role did they play in the evolution of the Himalayan metamorphic core, or the HMC. Now, to solve this problem, we needed to solve this problem to understand the Himalaya much, much better. And this brings us to the objectives and the rationale of the study. The first and foremost objective of the study was to map the MCT and its proximal shear zones based on structural features. And then the study was divided into two independent parts. The first part analyzed the role of fluids in strain softening within the MCT shear zone. And the second part focused on constraining the relative timing of the shear zones and to propose a new model for the evolution of the Himalayan metamorphic core. Now, when we are discussing about the first objective, what we have used is a conceptual framework of shear zones. Now, this study actually builds on the studies of several workers who have worked on the geometry of shear zones and have found out that shear zones typically show two distinct types of geometries. The first one is called a zone type geometry, where there is a deformed core marked here by the green color, characterized by the presence of ultramyelonites and myelonites, which are flanked by associated deformation zones of protomyelonites, here shown by the yellow colors. Now, the majority of the strain is being accommodated in the core zone, and a little bit of it is accommodated in the flanking deformation zones. Whereas the protoliths, which are marked here by the white colored rocks, they remain relatively unaffected by shear zone related deformation. Also, shear zones can show another type of geometry, which we refer to as island channel geometry. While channels of myelonites, they anastomose around relatively undeformed rocks, which we refer to as islands. Now, the myelonites have some typical characteristics. They have well-developed foliations and lineations. They have shear sense indicators in them, and they have smaller grain size due to dynamic recrystallizations. In addition to the conceptual framework of shear zones, we have used protolith signatures to identify the rock units on either side of the map shear zones. Now, this is again the geological map of Sikkim. These black bars indicate the transects that we took in different parts of Sikkim. So we took two transects on the northern part of Sikkim, in North Sikkim, from Dikchu to Lachen and from Mangan to Sakyong. In the eastern part of Sikkim, we took two transects, one from Gangtok to Nathula and from Rongli to Kupu. As you would see here, that I have not marked the locations of the shear zones in this study, in this map. What I'll do is I'll use the conceptual framework of shear zones to let me know where the shear zones are actually located. So my study revealed that there are three major shear zones. The first one, which is within the Greater Himalayan sequence rocks, it is named as the Chungthang Thambi Thrust, which we have named based on its type area exposed near the town of Chungthang and Thambi viewpoint in eastern Sikkim. As you can see that it is characterized by presence of shear sense indicators, in this case organs in mesoscale. And when we look at the thin sections, we can see that porphyroclast systems with well-developed shear sense indicators indicating thrust sense movement. And the myelonites in the eastern part of Sikkim, they have also been reactivated and they are surrounded by gouge materials indicating reactivation of the CTT. Now, the CTT is actually the equivalent of the high Himalayan discontinuity in Nepal, which was mapped by Karosi et al. Moving further south, we found our second shear zone, which we have termed as the MCT, because it transported the lower GHS rocks over the lesser Himalayan crystalline sequence rocks. Again, they have telltale signatures of the presence of myelonites, here indicated by SC fabrics, indicating thrust sense movement. And we also have plenty evidences of dynamic recrystallization. As you can see here, amoeboid shaped quartz grains, they indicate dynamic recrystallization in the grain boundary migration domain, whereas we see also chessboard extinctions in large scale, in larger grains of quartz, which are surrounded by smaller recrystallized grains, indicating subgrain rotation. And finally, we found a third thrust which transported the lesser Himalayan crystalline sequence over the lower lesser Himalayan sequence, which we termed as the Munchiari thrust from its type area in western Himalaya. As you can see again, telltale signatures of presence of myelonites indicated by presence of shear sense indicators and dynamic recrystallization of quartz. This thrust was mapped in other regions by Bhattacharya and Mitra. So to summarize our structural findings, what do we have? We have three shear zones, the CTT, which is within the Greater Himalayan sequence. We have the MCT, which transported the lower Greater Himalayan sequence over the lesser Himalayan crystalline sequence. And then we have the Munchiari thrust, which is within the lesser Himalayan sequence, transporting the crystalline lesser Himalayan sequence over unmetamorphosed lower lesser Himalayan sequence. Contrary to what previously it was believed, all of these shear zones have mappable signatures, and the Munchiari thrust, they show zone type geometry, whereas the MCT, it shows a island channel geometry and as well as zone type geometry. Thus, overall, it has an anastomosing geometry. Moving on, after our solving our first objective, our second objective was to analyze the role of fluids in strain softening within the MCT shear zone. A linear relationship exists between the log of the displacement of a fault and its thickness. Now, this was proposed by Hull back in 1988. When we plot the data for the MCT of different exposures of MCT, we find that the MCT is a strain softened zone in Sikkim, in central Nepal, and northwestern India. So our first question was, did fluid cause the strain softening? Now, when we look at the different exposures, rocks from the different exposures, we find that there are plenty evidences of fluid-induced alterations. We see here that plagioclase grains have been transformed retrograde to white mica, and foliation-defining biotites have been retrograde to chlorides. Again, here we see that potash feldspar has been altered to white mica and is surrounded by dynamically recrystallized quartz. Similarly, in the biotites have been altered to chloride, and these are for microphotographs from different exposures, so which gives us an indication that fluid activity was pervasive throughout the MCT. Now, moving on, what we did, we quantified the modal, the mineralogy of the rocks, that is the protoliths as well as the myelonites. What we found out was in the northern part of Sikkim, we found that the feldspar-rich rocks have been transformed to quartz and quartz mica-rich rocks. Whereas in the eastern transects, what we see that the feldspar-rich rocks have been transformed to very quartz-rich rocks. The quartz here being shown here in blue color, whereas the feldspar is being shown in this pie charts in the orange color. As you can see that, especially in the eastern part of Sikkim, the feldspar-rich rocks have been transformed to very quartz-rich rocks. Especially in the Lingdam transect, it is almost 100% quartz. So the paragneises and calc-silicates have been transformed to quartz and mica myelonites in the northern exposures, whereas the paragneises and orthogneisses has been transformed to quartz myelonite in the eastern exposure. So in conclusion, we can say that the fluid has transformed polymineral protoliths to mechanically weaker quartz-rich myelonites. And this was also attested when we did mass balance calculations. These mass balance calculations are also called isocone diagrams, where you plot the average composition of the myelonites on the y-axis and the protoliths on the x-axis. What we see is that silica enrichment took place in the Lingdam exposure, in the Kyungnosla exposure, and to a certain extent in the Mayangchu exposure. Whereas in the Lingza-Tolung exposure, the element mobility was more conservative. It gives us an idea that silica was either added from an external system or it remained immobile, whereas other elements were very mobile. So to conclude our understanding of the evolution of the MCT and the role that the fluid played in it, we proposed a three-stage evolutionary model. What we have is the first stage is the nucleation, where the large-scale shear zone like the MCT, they typically nucleate along pre-existing fractures. So as you can here see that the solid black lines, they represent the pre-existing fractures, whereas the green dashed line, it represents the proto-shear zone. Now, once the proto-shear zone formed, the strain localized within the shear zone as a result of dynamic recrystallization or dislocation creep, resulting in the formation of the protomyelonites. This is the development phase. Now, as the shear zone was developing, fluids infiltrated the shear zone, resulting in element mobility and resulting in inducing strain softening, which resulted in further strain localization and further localization of strain in the central part of the shear zone. Thus, the shear zone narrowed through time as strain was localized as a result of significant strain-induced strain softening. Fluid-induced strain softening, I'm sorry. So, as we see, these are the digitized photomicrographs from the different exposures. This is the tonalite orthonized from the lingdom exposure. The lingdom exposure is somewhere here. It has been transformed to quartz myelonite, whereas the paranises, the calc silicates, and the paranises have been transformed in other exposures have been transformed to quartz myelonite and quartz mica myelonite. So to summarize this objective, we have significant fluid syntectonic fluid activity, which resulted in reaction softening, quartz and mica enrichment. The myelonites were mechanically weaker than the protoliths. The strain localized within the relatively thin MCT shear zone. The MCT shear zone narrowed through time, and fluids did play a major role in evolution of the MCT shear zone. This study was important because this was the first documentation of fluid activity within the MCT shear zone. And taking a lead from this study, Kalita et al. Conducted a study in Arunachal Himalaya, where they found that the MCT zone in Arunachal Pradesh also exhibit significant amount of strain in fluid-induced strain softening. Now we come to the final objective of the study, that is to constrain the relative timing of the shear zones and to propose a new model for the evolution of the Himalayan metamorphic core. For that, I have used a multi-thermochronometric approach. I have used temperature-sensitive thermochronometers like monazite and garnet ages from published studies, which gives us an idea about the timing of the peak metamorphic conditions. Then we have the retrograde monazite ages and the muscovite biotite argon cooling ages, which was from our own study, which gives us an idea when the rocks crossed the 425 to 350 degrees centigrade isotherm. And finally, we also have the muscovite biotite argon recrystallization ages, which gives us the timing of the last stages of shearing. And finally, we have the apatite fission tract ages, which gives us an idea of when the rocks crossed 120 degrees centigrade isotherm. So basically what we have snapshots at different depths and at different times, and we can use these snapshots to reconstruct the entire history of the different thrusts. So using this method, I have plotted the temperature on the y-axis and the ages on the x-axis. This red star indicates the timing of the peak metamorphism. In this case, this is the hanging wall of the CTT. And we see that the CTT was active from 27 to 22.5 million years, which corresponded to a rapid stage of isothermal decompression to start with, followed by isobaric cooling. And the CTT was reactivated at around 13.5 and 11.6 million years, which you saw was the resulted in the formation of the gouges in the eastern exposure. Finally, we also find that the MCT was active between 22.5 and 7.2 million years. It showed a protracted activity, and it resulted in rapid cooling of the lower GHS rocks in its hanging wall. Finally, we come to the Munchiari thrust, which was active between 12 and 10 million years. And as you have seen, that the thrust activity of the thrust resulted in rapid cooling of the rocks, followed by a slower rate of cooling. So finally, to conclude, we have to find now what role did they play in the evolution of the Himalayan metamorphic core. We needed a new model because the existing models were insufficient, as they focused solely on one fault system, that was the MCT, which were placed at different locations. Before we go into the model, we need to find out also how the pressure temperature conditions varied in the different thrust sheets. We find that in the temperature, the peak metamorphic temperature, it increases upsection in all the thrust sheets, whereas the peak metamorphic pressure within the individual thrust sheets, they remain constant within the uncertainty. So what are the model constraints that we have? We have three shear zones, the CTT, the NCT, and the Munchiari thrust, which developed between 27 and 10 million years. The STDS, which is at the top of the Greater Himalayan sequence, was active between 24 million years and 13 million years. Also, we have out-of-sequence thrust, which called the Zema fault, which was active at the same time as the STDS. We also saw that the structurally higher thrust sheets were metamorphosed earlier and at higher pressure temperature conditions than the lower thrust sheets. And within individual thrust sheets, the metamorphic temperature increases upsection, but pressure remains constant. So with this, I have proposed a four-stage evolutionary model for the Himalayan metamorphic core. So following the India-Eurasia collision, the first stage was the underthrusting and prograde metamorphism of the upper and the middle Greater Himalayan sequence rocks. So the rocks in the Greater Himalayan sequence, upper and middle Greater Himalayan sequence, they underwent prograde metamorphism to start with. Now in stage 2, the CTT, the STDS, and the ZF became active. The CTT became active at about 27 million years, resulting in rapid upliftment or rapid exhumation of the middle and the upper GHS rocks, resulting in exhumation, as you can see here, from A2 to A3 and then A4. A2 to A3 is isothermal decompression, followed by isobaric cooling. And the rocks in its footwall, that is the lower GHS rocks, started undergoing prograde metamorphism. One interesting thing that we have to notice here, that since these hot rocks were brought on the cooler rocks in the footwall, it resulted in the inflection of the isotherms, positive inflection in the hanging wall side and negative inflection on the footwall side, which resulted in rocks in proximity of the shear zones to be metamorphosed at higher temperature but at similar pressure, and this resulted in similar pressure within the individual thrust sheets but at higher temperature in the individual thrust sheets. Now moving on, after the CTT became inactive, the NCT became active at about 23 million years, and it continued its protracted activity till about 7.2 million years, resulting in exhumation of the lower GHS rocks and prograde metamorphism of the LHCS rocks in its footwall. And finally, after the NCT activity ceased, the Munchiari thrust became active at about 12 million years, resulting in rapid exhumation of the rocks in its hanging wall. Finally, what we have is, after the Munchiari thrust became inactive, the lesser Himalayan duplex started growing and resulted in passive upliftment of the thrust sheets on top of it. And this is the present day configuration of the different thrust sheets. As you would see that they are juxtaposed laterally, although after erosion, although they were juxtaposed on top of each other to begin with. This gives us an idea that the so-called inverted metamorphic sequence, which was thought to be part of a single sequence, is not a sequence but a juxtaposition of different thrust sheets which were metamorphosed at different pressure temperature conditions. So the salient features of this evolutionary model are: it reconciles with the available structural information and earlier metamorphism in structurally higher thrust sheets at greater pressure temperature conditions. We have sequential metamorphism and exhumation of the thrust sheets. The thrusting is what that controlled metamorphism, and it was substantiated by the coeval nature of prograde metamorphism in footwall with retrograde metamorphism in hanging wall. So this model is totally different from the models which were proposed earlier for the inverted metamorphic sequence or the metamorphism of Sikkim. This left model in the left is from Mottram et al., which suggested that there were a number of imbricates in the footwall of the NCT, which resulted in formation of the inverted metamorphic sequence. But the structural recognition of this imbricates have never been found till date. Also, this is another model, the inverted metamorphic sequence model of the channel flow, modified channel flow model by Chakraborty et al. This is Sumit Chakraborty, who suggested that a partially molten channel resulted in metamorphism of the lesser Himalayan sequence, and then it got inverted. However, we do not find that the unmolten rocks, they do not form part of, they are part of different thrust sheets, they are not coherent, and no evidence of the imbricates have been found till date. So the proposed model, should be better constrained structurally, and they don't have good structural constraint. So finally, to conclude, the major takeaway points from the conducted study was that there are three major shear zones in the Himalayan metamorphic core of Sikkim: the CTT, the MCT, and the MT. The CTT is the equivalent of the HHD mapped in Nepal. All the shear zones, contrary to previous notion, show mappable signatures characterized by presence of myelonites. Significant fluid-induced strain softening in the MCT shear zone resulted in mineralogically and compositionally different myelonites than the protoliths. The CTT, the MCT, and the MT developed in sequence, and the Himalayan metamorphic core developed as a consequence of exhumation due to southward propagating thrust system. And the inverted metamorphic sequence, which has attracted a lot of attention from several metamorphic petrologists, is not a sequence but is formed due to juxtaposition of different thrust sheets. So after concluding the study, I'll just briefly show you what are the future directions in which we can conduct further studies, which came as a byproduct of this study. For example, the region between the CTT and the STDS is still not constrained well enough structurally. So we still don't know whether there are further shear zones in this region, and what is the overall structure of these shear zones. Do they form part of an imbricate system or a duplex? It would be a worthwhile work to actually explore this problem in detail. Finally, the model needs to evolve accordingly as we get more and more data from the field. And when we compare our findings with neighboring areas, we find that we have in-sequence thrusts in northwestern Himalaya, central Nepal, and eastern Nepal, and in central Nepal, whereas in eastern Nepal and in Sikkim, we have in-sequence and out-of-sequence thrusting in the greater Himalayan sequence. Whereas in further east, in Bhutan and in far eastern Himalaya, in Arunachal Pradesh, we only have out-of-sequence thrusting. So what we need to understand is that why this variation in kinematics across the Himalaya. So the reason can be that there is variation in kinematics across the Himalaya, and probably Sikkim and eastern Nepal, they represent a region of transition between two different regions like the central Himalaya and the far eastern Himalaya, which have different kinematic history. Also, when we compare the ages of activity of the MCT and the Munshari thrust across the Himalaya, we find that they vary non-uniformly. So one of the reasons for that can be that there are transverse structures like the Gish fault, the Yamuna Tier fault, which may have segmented the Himalaya into independent regions, and the different regions of the different parts of the Himalaya may have evolved independently from each other. So we need to find answers to these questions to understand the Himalaya much better. Also, I'll briefly touch upon another point that is very interesting. That is, the current models in the Himalaya, they implicitly assume plane strain deformation. That is, all the deformation occurs from north to south. But we see well-developed shear sense indicators in the east-west planes as well. Sorry for that. As you can see here, in the northern part of Sikkim, we have thrusting in, we see well-developed shear sense indicators on the north-south plane, whereas in western Sikkim, we see well-developed shear sense indicators on northwest-southeast planes, and in eastern Sikkim, we see the well-developed shear sense indicators in the east-west planes as well. This indicates that there is significant origin parallel deformation as well. Now, the implicit assumption is that all the deformation has taken place because it is plane strain. It has taken place on the north-south plane, indicated by this black arrow here, which would indicate that the stretching lineations should all plunge towards the north. But this is very difficult to understand because majority of the rocks exposed in these regions are S-tectonites, that is, they lack any stretching lineations. So we cannot straightforwardly analyze the kinematics in these regions. Also, the presence of shear sense indicators in different parts of Sikkim highlight that there is significant deformation occurring from northwest to southeast in the western part of Sikkim and from west to east in the eastern part of Sikkim. So we need to analyze the three-dimensional deformation in the orogens as well. So this is the step ahead in front of all of us. And my research group and Professor Mamtani's research group, we have been pursuing this problem in detail, and we are making some significant progress in this. So with this, I would like to conclude my talk, and thank you for your attention.
Thank you very much for this excellent talk. So now I would ask the audience if they have any question. Anybody from the audience? Okay, Shantan,
Yes.
just since there are quite a good number of undergraduate students are here, I would request you to elaborate 2 points here. First one, the general idea about the Himalayas is that as we move towards south, gradually we get the younger thrust, and particularly when you are talking about MCT, so across MCT there is inversion of age, isn't it?
Yes. Inversion of the protolith ages, not the metamorphic ages.
Protolith age. And you were talking about DCLS model also. So just I would request you to elaborate this particular point, particularly for the undergraduate students. Okay. And for their better understanding, please mention another thing, that what is the difference between your in sequence thrust and out of sequence thrust.
Okay.
These 2 points. I think the undergraduate students must appreciate this properly.
Okay. So I'll start with what is in sequence and out of sequence. So when the mountain belts they form, they start from the, as we know, the first stage is the subduction followed by collision. Now the inception of the mountains, they start from the accretionary prism. Now the accretionary prism is wedge shaped. Okay, it is like a wedge, and that controls the shape of the mountain. This is the thicker part is the hinterland side, and the thinner part, the wedge part, is the foreland side. Now what happens is when you have shortening as a result of collision, we have different thrusts developing to accommodate the strain. Now the first thrust, it develops on the hinterland side. So this is thrust A, for example. It develops first. Then we have thrust B. Then further down we have thrust C. Now this sequence, it develops in a sequence. Okay, it is propagating from the hinterland side to the foreland side. So this we call as in sequence development of thrust. That is, it is happening in sequence, like A, then B, then C. Okay, now what happens is sometimes there is another thrust. So we have A, B, and C. D should ideally, if it is in sequence deformation, D should ideally form somewhere further down, okay, structurally further down towards the foreland. But that does not happen. D occurs somewhere here in between A and B. This is called out of sequence deformation. That is, the sequence is not followed any further. We have out of sequence deformation. So this is a way of how the mountain keeps its taper angle. That is, it maintains its growth. So for that you have to study a little bit about critical wedge model, but this is the simplistic understanding of what is in sequence and out of sequence deformation. Now coming to the second point which sir said, that is, I think, a critted terrain model you are talking about, right sir?
Yes, sir.
Yeah. So ideally, what we have, when our thrust comes, it comes from the depth. Okay, it comes from the depth, and it juxtaposes rocks of two different grades. Now, when a thrust is bringing materials from the depth, it is ideally assumed that the rocks which are at depth, they are older than the rocks which are on the surface. So we have the older over younger convention for thrusts, but that is not maintained in the Himalaya, and particularly not in case of the main central thrust. If we look at the ages of the Greater Himalayan sequence, which is on the hanging wall side of the main central thrust, the ages, they vary from 500 million years to about 1200 million years. Whereas the lesser Himalayan crystalline rocks, which are in its footwall, they have protolith age of 3600 million years to about 1900 million years, and nothing is younger than 1700 million years. So that challenges our understanding of the thrusts, that is, the convention doesn't hold true. So how to explain that? Obviously, that means that the Greater Himalayan sequence is not the basement as it was previously thought. So what had happened was, Desels, what he suggested, that after the breakup of the Gondwana, the Indian plate started moving towards the Eurasian plate, and it docked with a terrain which was, lying somewhere in between, which resulted later into the formation of the Greater Himalayan sequence. It just brought it along with itself, and then it collided with the Eurasian plate. Now, since this was a accreted terrain, that it was not associated with the Indian craton, it got accreted with it along a suture, which later reactivated as the main central thrust. And finally, sir, if you don't mind me asking, what was the third question that you had in mind?
Yes.
What was the third question that you asked me?
Not third question. I just told you to explain these two particular points. Okay. So you have already explained, and I think the students got the points clearly.
Okay.
So, do you have any other query?
Yeah, if you have any other query, please ask me. I would be happy to answer them.
Please come out. Why are you so shy?
Chandana, that is a great talk, I think. And I must ask you a question that
Yes.
You told that the fluid, obviously, that was responsible for strain softening, right? So I think what type of fluid it could be? I mean, this is
Okay.
aqueous
Okay.
fluid or something else?
So at this point of time, we do not have much knowledge about the nature of the fluid. Okay, because for that, what we had to do was whether it is a meteoric fluid or whether it is coming from the deeper crust. For understanding that, we had to do some stable isotope study, but we could not do that for the time. But what is my understanding is that since those fluids were very siliceous, they were very silica rich. They were probably derived from the dewatering of the lesser Himalayan sequence rocks in its footwall. So when the thrust came, it deposited rocks on top of the Greater Himalayan sequence rocks on top of the lesser Himalayan sequence rocks, right? And that resulted in some dewatering, and the siliceous fluids resulting as a product of that, since shear zones are dilated, it just infiltrated the shear zone and resulted in precipitation of the silica, which we see, which resulted in the formation of the very quartz-rich myelonites that we see in Sikkim and in Arunachal Pradesh.
Okay, in most cases, I think in previous studies, in 1980s, there were experimental constraints on the fluids on deformation, on the specifically ductile deformation, and in most cases, it was found that the fluid is, I think, H2O rich.
Yes, that would be my understanding as well. But since we do not have much,
I think
constraint.
I think that could be done by direct fluid inclusion study. I think.
Yes. That was a point that was made to me earlier also. But since we were not really focusing on that part at that time, maybe this is an interesting, feature that we can look into in the near, in the foreseeable future. Yeah, I'm glad that you raised this point, and this would be something worthwhile to look at.
Is another thing is that
Yes.
the composition of the fluid must be different. I think if you compare the paranise and the calcilicate rock, because
Yes, yes. You are absolutely right, and because the nature of the fluid rock interaction is different, so obviously the nature of the fluid, and it is quite it is obvious. I think that in such a wide region which is spanning for about 40 kilometers along structural distance, we cannot have the same composition of the fluid.
yes,
So
obviously.
so the fluid rock interaction, if you look at a very smaller scale, also it would be variable. So yes, I think you're right, and this is another problem that I think Kathakali Bhattacharya and some of our students are looking into this problem. If I'm not wrong.
Okay.
But they are looking mostly on the Munshiari Trust, not on the NCT. So
Okay,
that
okay.
yeah, but it would be a worthwhile problem to pursue. I would be interested in pursuing that problem. Yeah.
Because
Thank you for that input. Yeah.
okay. No, another thing is that you said that most of the litho units have been transformed to quartz-rich
Yes.
layers.
Yes.
So that would be also interesting to
Hmm.
constant actually what type of methods are involved to such
Yes.
transformation.
Yes, that is, and when we published the Journal of Structural Geology paper, the idea was to give a brief overview of what is going on, but in detail, like what are the reaction textures and
Yes,
what are
obviously.
the
Yes.
retrogression features, what
Mhm.
type of element mobility is occurring in micro scale. These would be interesting problems to pursue, but again, for that, different people with different backgrounds need to come together
Yes,
because
obviously.
I was working alone, so that was a one person's work. So yeah, it would be an interesting thing, but yeah, something which is there in the back of my mind and something that I would like to go back and pursue. So if you are interested, I would happy to have you on board for this work as well.
Okay, thank you.
Yeah, yeah. Any other questions? I would be happy to take them.
Sir, sir, what about the Vaikrita thrust?
Vaikrita thrust is actually the MCT. If you look at the Vaikrita thrust in the northwestern Himalaya, it is MCT. Vaikrita thrust was originally defined by Valdia back in 1980s. Okay, and later when Talat Ahmed and his team started working, they found out that it is the MCT because it juxtaposed the greater Himalayan sequence over the lesser Himalayan crystalline sequence rocks based on the isotopic signatures. In field, it is very difficult to determine whether a rock belongs to greater Himalayan sequence or lesser Himalayan sequence because both of them are metamorphosed to amphibolite facies. So the only way of determining that is by using detrital zircons or by isotopic signatures, that is epsilon Nd or epsilon hafnium. Well, was I able to answer your question?
Yes, sir. Thank you, sir.
Okay. Any other questions?
Sir, has the Himalayan orogeny stopped or it is still going on?
No, it is still going on. There are plenty of evidences to suggest that it is still going on, and it will continue to go on until and unless the rift in the Indo-Australian system continues to grow. So as long as the rifting is going on, the subduction has stopped. What is going on right now is the collision. So if you look at general newspaper articles, you would see that the height of the Mount Everest has grown. Right, so it is to suggest that the Himalaya is still very, very active.
Okay, sir. Thank you, sir.
Okay, so any other question? So we have come to the end of this session. So now I would request Srijata to propose a vote of thanks. Srijata,
Yes, sir.
please.
I feel privileged to have this opportunity to propose the vote of thanks. On behalf of the Geology Department, Durgapur Government College, and my own behalf, I express our deep sense of gratitude to our honorable speaker who spared time from his busiest schedule to enlighten us with his lucid and thought-provoking speech. This will surely be encouraging us in our future endeavors. We are thankful to our honorable principal for permitting us to organize this lecture. Last but not the least, I take this opportunity to thank the House of Audience who graced this occasion with their presence and active participation. Thank you all.
Okay, so
So,
big hands to Sayantan.
uh, so,
Yeah,
sir, I would like to take this opportunity to thank you for giving me this opportunity to speak to the students and to interact with the fellow colleagues. And it was an opportunity for my students also to attend the talk. And I would also tell the students who are present here that there is always an opportunity if you are interested in working on the Himalaya or the Indo-Burma wedge, if you're interested in structural geology, not the conventional structural geology because things are changing very, very fast. You can come and join our research group. We would be happy to host you in any way, shape, or form.
okay. Thank you very much, Sayantan.
Thank you so much, sir.
Okay.
And it was good talking to you after some time.
Thank you.
Thank you. So I'll leave the meeting with your permission.
Okay. Okay,
Okay.
thank you.
Thank you so much, sir.
Okay.
Thank you. Bye.
So bye to everybody.
Bye.